Thanks, Binkai, for the introduction, and thanks, Dominic, for inviting me to this great department to share some of our research. So I'm going to talk about optimizing treatment decisions. It's probably the concept of tailoring treatment is probably very familiar to a lot of you here, but specifically, I want to talk about mental health. So I work with mental disorders. So for mental disorders specifically, if we treat patients using one-size-fits-many care model, it's going to be very inefficient. The response rate for a single course of, say, antidepressant treatment is only 33%. So only 1/3 of patients will respond, and the relapse rate is also high. So one of the sources of this inefficiency and inadequate treatment is heterogeneity of disease, right? Mental disorder is, if you talk about a broad category of what's called a depression, then the diagnosis is based on symptoms only currently. So if a patient has 5 out of 9 symptoms, some of them listed here, they will be called having depression. However, there are a large number of combinations of symptoms you can satisfy this criteria. So there are more than 200 combinations. So phenotype-wise, phenotypically, or symptomatically, there are many heterogeneity of what's called a depression. And also biologically, there are many risk variants identified. This is slightly older data, but already there are 44 independent risk variants. And if you look at a clinical course, you look at how patients develop a disease, how they recover. So everybody will have something slightly different course of recovery, of getting disease, recovery, relapse, and so on and so forth. So all these sources of variability contributes to heterogeneity. So to deal with these challenges, NIMH has this precision psychiatry conceptual model. So one hypothesis is that if we can somehow reduce this heterogeneity of disease by measuring disease more precisely, maybe we can parse out all different variabilities. So they propose this research domain criteria, RDoC framework, to look at all different levels of measures, tapping onto all different domains of mental disorders. So they are saying like, let's think about what are the important latent constructs of the disease. So they came up with all those 6 different constructs, including negative valence. This would be something like fear, anxiety. Positive valence would be something like how patients value different sources of stimuli, how they react, and what's their value system, what's their reward function, and so on and so forth, cognitive and also. So corresponding to each of those latent constructs, there are measures at different levels, all the way from molecular level to cell to the brain circuits and to behavior and self-reports. These would be clinical clinician-assessed measurements or patient self-reported symptoms. So each of those levels of measures will tap onto those different latent constructs. So by reorganizing our measures, our thinkings of mental disorders, the hope is that we can target the treatment according to different impairment at the different levels of the different domains and using different levels of measurements. So this particular conceptual model says that let's look at the brain circuit level measures. And if a patient has more impairment in, say, default mode connectivity, maybe they should be treated with a TMS, transcranial magnetic stimulation. If they have salience, more impairments in the salience network, then they should be treated by SSRI or deep brain stimulation. Or if they have impairment in negative affect network, then they should be given CBT, cognitive behavioral therapies. So by targeting this therapy according to impairment at the different levels and the different constructs, we can improve the efficiency of treatments. So that's the whole conceptual model for precision medicine. So there are several empirical studies launched to empirically test those hypotheses, to test this model. One of them is so-called EMBARK study. It's a 4-site big study. It's big, but only 200 patients. It's for depression study, 4-site. I believe Michigan is one of the sites and Columbia is one of the sites. So they collected a whole range of different measures that will tap on all those different domains and looking at how do we look at moderators and create biosignatures of antidepressant response. So the current practice in clinical studies is still hypothesis-driven, right? Testing for moderation, look at the HTE based on predefined subgroups, or look at hypothesized treatment moderators. But we all know that this testing, quickly you will run into this multiplicity problem, multiple testing problem. And also, if you ask clinicians to come up with a list of predefined subgroups, sometimes it's a little bit difficult, right? So in the EMBARK study, we do have tier 1 variables, tier 2 variables, tier 1 moderator, and tier 2, and so on and so forth. If you test one by one, it's going to be very inefficient. So there are, in the grant, actually, it was proposed to look at some machine learning methods for the discovery phase to discover multiple moderators together and come up with, probably we can discover complex nonlinear interactions between those moderators. What can we use them to tailor treatments? And these machine learning methods right now are being also proposed to be applied to psychiatric studies. And one example of some of these methods might be useful would be, say, EHR, Precision Medicine Initiative, with a diverse range of different measures. So these methods are probably capable of handling different types of data modality. In psychiatry, it would be wearable devices, neuroimaging, and biological measures, and more importantly, behavior phenotypes. So they are also being made popular because we have many available high-quality implementations of cutting-edge machine learning methods. But if we want to directly apply those methods to optimizing treatments, that's not going to be very helpful, because a lot of those problems are causal related, right? We don't get to observe both potential outcomes. So it's not a direct application of supervised learning. And if we want to learn both the RDoC constructs, how we map measures to the latent constructs, and how do we tailor treatment together, then it's both the disease subtyping and association with treatment response. You can think of it as both supervised and unsupervised learning. We want to do both. And also our data size is pretty small compared to other machine learning applications. In our EMBARK trial, there's only 224 patients, and it's very expensive to obtain everybody's neuroimaging measures. So you run into this sample size problem. Applying any deep learning directly would not be feasible. And also, we don't want black box treatment rules. We want to balance both those interpretation and also with flexibility and accuracy. And also, these applications have high impact, so we care about robustness and generalizability. So bear in mind these background. I will share some of our work on how do we tailor treatments using ITRs, individualized treatment rules. So there are many recent methods developed in this space, too many, so I didn't list every single one, but I just refer to this book. But many of them, most of them actually work on the observed variables and also single outcome variables. For mental disorders, this you already see that we need many measures and many aspects to more precisely characterize disease. So if we just have a single outcome in the reward as a reward function in, say, learning ITR, it's not optimal. So that would not capture heterogeneity across individuals, assumes that those heterogeneity is explained by observed factors only. But in mental disorders, this is a Disney plot for many baseline variables for 3 depression trials. You can see that there's probably a lot of hidden heterogeneity once you reduce those multidimensional baseline covariates into this 2D space. And there are probably different kind of mapping, different heterogeneity captured by unobserved variables. So we want to capture those, use latent factors to parse out their contribution to variation in mental disorders. So our goal is to account for this heterogeneity due to both observed and hidden patterns, hidden variables, hidden latent variables for the tailoring variables and also the outcome. So to give you concrete ideas, this is a depression measure, HAM-D depression measure, sometimes used as gold standard primary outcomes in clinical trials. So these are 17 items. So it's shown here 15 items. They actually have a lot of patterns of different items used to measure depression. So they fall into different categories: atypical, sleep, insomnia, core emotional, and so on and so forth. So these fall into the regulatory, arousal regulatory system. And some of those core emotional are both negative and positive valence system. So to accommodate so if you use a single outcome as your primary outcome for ITR learning, you would be mixing patients for example, has more impairment in atypical, less in core emotional, with the patient has less atypical and more core emotional, because their total sum of different symptoms will be the same. So you would not be able to parse out different variation or different heterogeneity that's carried for the depression. So we want to look at this from a different perspective. We want to look at what's used in psychiatry for measurement models for measuring diseases. So there's a long history of using latent variable models for mental disorder to characterize outcomes. So we want to integrate those measurement models with the machine learning models to learn multi-outcome, multiple item related outcomes and for ITR learning. So we build those ITRs also to target those latent mental states. For example, caps onto those latent constructs instead of something that modifies the observed variables. And also by doing this, we would be able to say capitalize on the correlation among different domains and different symptoms to reduce the noise and increase reproducibility. So the way we do that is to look at, for example, first of all, how do we represent those different depression items ranging from 0, 1 to 4? Say there are 15 baseline measures of depression, and we actually use the k-binary latent mental states to do the representation learning of those 15 different symptoms. For example, the first one could be activation status of negative emotion. So if Z1 is activated on in the on status, is a binary on-off status, then it would increase the chance of observing several negative symptom related observations. So these are latent variables, latent mental states used to lower dimensional usually, used to capture all the major variation of the different combinations of the depression symptoms. And then after treatment, we would have those latent variables corresponding, we call them latent potential mental states after taking treatments A, and they also will be reflected by the outcomes observed after treatments, depression symptoms. So observed symptoms, all of them are basically the reflective indicator of the latent states. And activation status of latent potential mental states after treatments will also be related, controlled, or by the baseline tailoring variables. So that's a conceptual model. So there are several important assumptions in this model. The first one is in the measurement model, it's called a local independence, or it's a conditional independence assumption. It says that in this part, given the latent states, the observed measures, they are conditionally independent of each other. So you see connections from latent states to each of the symptoms potentially, but you don't see connections or edges between observed symptoms directly or between latent domains, latent states directly. So this is a conditional independence assumption. It basically says that all the correlation we want to measure are captured by those groups of the latent mental states. And then the second important assumption is invariance assumption. It says that the treatment, what is changing is the activation status of the latent states. The treatment does not modify how we measure those latent states from observed measures. In other words, those weights, you see that before at the baseline and after treatments, they stay as constant. So those W, those weights. So that's saying that if we have a stable instrument, then this instrument should be having the same weights of how they measure the latent states should not change. If Z1 is latent states for controlling negative symptom before the treatment, after treatment, we still use Z1 as the latent nodes corresponding to the negative symptoms. So it's controlled by those fixed weights before and after treatment. So this is going to be one assumption we'll be using when we learn the ITR for tailoring those latent states. And then the goal here is to learn an ITR that can optimally change those latent states. So we want to, the first stage of that, it's a two-stage process. The first stage is actually to learn this representation model, right? So to learn this representation model, if we think about some fully non-parametric model, just have 15 HAM-D items and 2 latent states, we already have billions of parameters. But we all know that as statisticians, this is not necessary at all, because a lot of combinations will have a very small, what we observe is a very small subset of all those non-parametric different combinations. So we should be able to describe this model, say a big we don't need to use those fully non-parametric models to describe observed data of depression symptoms and the latent mental states. So we at that time when we work on this paper, we use this so-called restricted Boltzmann machine (RBM). It's actually a probabilistic generative model for modeling discrete random variables, joint distribution of discrete random variables. So originally it's designed for binary nodes, and it's a building block. Some of you may be very familiar. It's a building block for a lot of deep learning models. If you stack them together, you can do unsupervised learning with binary or discrete random variables. And also, I will show you later that it satisfies this measurement model assumption, and it's very interpretable if you just use a two-layer RBM. And it has a very quick approximate learning algorithm, easily scaling up. So this is a visual of representation power of RBM. So I'll show this a little bit later. This is actually a temporal RBM. We modified a static RBM to the temporal RBM. This is the EMA measure, ecological momentary assessment measure of 30 days for depression and anxiety patients. So on the left is the observed data distribution for the observed data over time. So patients rate their depression or their each questions on the mobile phone, and we collect them for 30 days. And on the right hand is after learning from this model, we generate data. This is a model generated data. So it looks like this temporal RBM can faithfully represent the observed data, both also represent their dynamic patterns. So in this project, we were more interested in modeling the dynamic patterns. So the postdoc and student who work on this recent paper, they got really excited about a month ago, because we all know that two computer scientists got Nobel Prize in physics. So they looked up their major contributions. So actually in their major contributions, one of the contribution is this RBM model they used in their project. So they got really excited. So this is an illustration from the Royal Swedish Academy of Sciences. It's not a great illustration, but that's what they have officially. So this whole upfield network is a fully connected network with only observed variables. Those are all binary variables, 0, 1. And then this Boltzmann machine is a two-layer model, observed layer. It has an observed layer and a latent layer. So the bottom layer here, they are all latent variables. All of them are binary variables. A restricted Boltzmann machine just built some Boltzmann machine, but removed all the edges at the same layer. So it satisfies this conditional independence assumption, what we want from the measurement model. So, and then it's the RBM model here. And then mathematically, it's modeled uses the so-called energy function. So energy, maybe that's why they were given Nobel Prize in physics. So this Boltzmann machine, I don't know, but the conjecture has an origin in physics. So they're used to model physical systems. And if a state has a high energy function, then they are not stable. So we have less chance of observing that state. So you see that this phi energy function has a negative sign here. So they use this form to model joint distribution of those binary random variables. So all the art here for your specific system you're modeling, or the science here, is to design an energy function that can capture your observed variable. So in RBM case, we see that this is second order interaction between observed nodes Y and latent nodes Z. So you only see second order interaction here, but not within any other nodes of Y, not between the latent nodes Z here. So those two interactions, those two second order terms are missing. So in our case, because we have ordinal measures, we actually use this proportional odds model variation of RBM. So we assume that we can use those, they're interpretable because that those weights W or omega here, J, K, you can show that if we design energy function in this way, then WJK here is the odds ratio between the kth latent nodes, their odds ratio on activating the jth observed nodes. And those WKJK does not depend on a category P. So you can efficiently use a proportional odds model to model different ordinal variables. And you can use those WJK to interpret what your latent variable, latent mental state is representing by looking at a map or the weight or all the learned weights, WJK. So in this case, that's the basic model. And then the parameter learning is by maximizing, of course, observed data likelihood. But that's very difficult because we have all discrete random variables. So this likelihood is going to have a nasty normalization constant. If you have many variables, it's infeasible to calculate, to enumerate all the different combinations and calculate this term, this C term. So one of the major contribution from Hinton is to propose this so-called contrastive divergence algorithm, CD algorithm, to bypass learning this constant, normalization constant. So we can just show that we can re-express the likelihood gradient with respect to, say, these weight functions, W, alpha, and beta, by two terms, two conditional expectations. One is a conditional expectation of latent variable given observed data. The other is an expectation given a model. So he proposed the MC sampling given data, another sampling given a model, take the contrast or the difference between those two expectations, then you can get a gradient. And based on this form of the gradient, we don't have to calculate normalization constant. So easily you can very fast calculate, learn those models, learn all the parameters in the model. So this is a model learning part. And then we have to determine the number of latent states. We chose this either based on we know how many factors may contribute to depression symptoms, or you can, because it's likelihood based, you can use AIC or BIC to determine the number of latent states. And then that's the representation part. So another key part in the middle here is to learn those ITRs. So if learning for ITRs, we still need something to measure how the quality or the outcome of after applying these ITRs, right? We still need some numerical values to summarize the outcomes. So what we proposed in the paper is to have a summary of the latent domain, latent mental states. So this function can be, say, a simple average. But if we have a targeted approach, we want to target each different domains of the mental disorder, you can choose a different G function. So this is assumed to be known, but we later on propose a method to learn this G function. How do we aggregate different latent domains from data? So for now, we'll assume that G is a known function. So once you have this known function to aggregate the different mental states, we have our outcome here. Based on the latent mental states. So the difference is that our outcome is not observed the Y1 here, but a function of the Z1 here. So the challenge is that if we have a lot of approaches, if outcomes are observed, but for latent G, and then what we think that we need to do is that we need to have a surrogate function that's based on the observed outcomes Y, but they have the same conditional expectation. Because after all, ITR learning is about maximizing this conditional expectation of outcome given tailoring variables X, given baseline depression symptoms Y0, and how do we get a treatment rule that will maximize, optimal rule that maximize this outcome. So since we only need a conditional expectation, then we can construct so-called surrogate outcomes based on the invariance assumption. So we can show that mathematically, we can construct the G tilde if we're being smart or being careful about how we choose this G tilde. And this G tilde function will capitalize on the invariance assumption because this part only involves baseline variables. So this baseline Y0 are all observed. And by this invariance assumption, after we learn those weights W, we can construct, we can use a matrix form and construct a surrogate outcome, which has exactly the same conditional expectation. So that's how we get by without knowing all the latent variables, Z1. So after our first step of representation learning, we have the weight function. So we construct the surrogate outcomes. And then we also extracted those latent tailoring variables representing latent mental states at the baseline. We use them also as tailoring variables into learning the ITRs. So once we have all these, we can use any of the recent developments in learning ITRs, whether you use Q-learning or augmented O-learning and so on and so forth. So in our case, we chose to use a previous method developed use augmented O-learning. We looked at some theoretical results not shown here. But I want to show you what happened when we applied this to the EMBARK. So in the EMBARK, in the baseline learning part, the first step, we actually borrowed another study trial, another trial for depression, because we think by enlarging the sample size, we can learn something more representable, more generalizable from larger sample of patients. So you can learn your measurement model using a more representative sample. That's going to be increase your reproducibility of the learned ITR. And here are some additional tailoring variables in addition to baseline symptoms. So the cognitive system, we use the flanker test. And for the negative valence system in the RDoC construct framework, we use a neuroticism scale. And we determined 3 latent states by BIC, also consistent with the previous literature. So the interpretation of 3 latent states, one is actually, I already reviewed the patterns to you already. That's actually learned from our data. So one is a sleep-related patterns, and one is a core emotional, and one is atypical symptoms. And we found that those 3 latent states can divide patients into 8 subgroups by determining their on and off status. And they're actually very different. So we can show that visually, these 8 groups are quite separated. But more important, this can be viewed as unsupervised learning, right? But an important question is, are these latent subgroups related to the treatment response? So when we look at that, we use a variable, external variable for evaluation. So this responder status is evaluated by clinicians. So we're not using, our outcome used in the learning is only HAM-D symptoms. So this is an external validation outcome. So you can see that by using the ITR compared to standard approach without using only the total sum as your outcome, we have a little bit of improvement in the response rate. And we have a little bit of decrease in the sum of HAM-D after treatment. So the lower, the better. But what's more interesting, what we learned is that these are learned important tailoring variables, age and cognitive control system. And also these are the subgroups. So we learned that these subgroups are quite related to predicted optimal treatment assignment. So this coloring, purple is predicted to be optimal for antidepressant, those patients. And for those patients, antidepressant doesn't help them. So they don't gain. So we actually found 15% of patients were recommended to placebo only, and they have a quite high response rate. So it shows that we found a placebo responder group. And another group defined by our 3 latent states, they have less atypical symptoms, and mostly they were recommended as having antidepressant as optimal treatment. So we found a subgroup of antidepressant responders. And there's a mild group also, they are antidepressant responders. So their response rate were much higher than one size fits all rule, and also the ITR overall rule. And then interestingly, we also found a group, the most severe group, they are not responding to antidepressant. Even if you give them antidepressant, their response rate is very low. So it's important to find these groups of people as well, so we don't have to give them antidepressant. So no matter, although we found some subgroups, but overall, the response rate is still at no matter what we do, is only half, 49%. So we're thinking hard about what's missing here. Of course, you can think about, say that this treatment just hits its ceiling, maybe we need a different kinds of treatments. we need to develop other kinds, new generations of antidepressant, or you even need to go with deep brain stimulation or other type of treatments. But given the data we already have, we think, we're asking whether there's room for improvement. So one direction is to look at other modality of tailoring variables, right? In addition to what we already have, can we extend this RBM model, not just for symptoms, but including also continuous variables, including neuroimaging. So in this follow-up paper, we looked at, first of all, whether by expanding the measures, can we get any improvement? Second of all, does deep learning model help? So in this approach, what we found that, well, it helped a little bit, but not a whole lot. But what's nice is that by including additional measures, it seems like the proposed method is more robust, having outperforming other types of some deep learning models on a range of outcomes, not just HAM-D, but also some external outcomes. And also another direction is to look at, I already showed you that the G function, should we use subject specific? Should we learn those aggregation function from the data? I get this question a lot when I present this talk. How do you come up with aggregation function that everybody agrees? It seems that clinicians may not agree upon which latent mental domain is more important for tailoring treatment, right? Do I want my patient only to improve on certain treatment, a certain domain? So what we did here is to learn this G function from the data using another external variable, which is the overall responder status. So we're looking at which domain, how do we construct a summary of those all latent domains such that expected value of this latent domain is going to be the same as an overall variable of measuring the overall responder status. So, and also we let this G function to depend on the patient-specific covariates. So these baseline covariates are certain things as patient preference. So before the treatment, there's a variable asking, one of the trials asking patients, do you prefer which kind of treatments and what type of treatments do you think you will gain, you will most benefit? You can use those variables to see for different types of patients, should we aggregate their mental state, latent state differently to get the similar overall responder status? Responder status. So we did this extension to using data to estimate those G function. They're subject specific, so we call them like a personalized weights. And then finally, what we learned is that we putting also neuroimaging measures still come up with the 3 latent states. And so one of the latent states now is highly representing the imaging measures, and others are representing the core symptoms and also the contrast of the imaging measures. And another one just combined the regulatory and some atypical symptoms. And we were able to also get robust improvement on a range of final outcomes. So that's a second improvement we think might help towards a direction. And then to better use those imaging measures, what we did now in the most recent work is to really use capitalize on recent developments in variational autoencoder VAE models, but we use a supervised VAE model, SVAE model. So VAE model usually just for reconstructing purposes, right? So you put in some faces, you get the reconstructed faces, and so on and so forth. So in this case, because EEG measures are emerging as one of the useful tailoring variables for depression. So what we did is that we used a neural network specifically designed for EEG measures that has both the temporal filters and also the spatial filters, and then also a separable convolutional layers to take into the interaction between spatial and the temporal features. So but this method is just designed for a deterministic model to feed forward the deep learning model, and their outcome is just responder status or clinical outcome. So what we really want to learn is HTE or ITRs. So what we did is that in addition to VAE reconstruction loss function, we also introduced this ITR-based loss function. You can treat those value functions as a supervised VAE, add another loss function to the original VAE loss to let the VAEs to be supervised. So the learning of those feature maps and also weights in the neural network will be supervised by your outcome part. And the outcome part is this ITR learning value function, or you use some other type of HTE learning functions. So in this case, we were looking at some initial results. So for the initial results, for predicting response, actually this VAE-based method quite outperformed directly deterministic EEG-net. And for learning HTE, if you look at the response rate on a subset on two sites example, because another site has a really poor EEG quality measures, we didn't include those, actually quite improve upon the policy tree and also one size fits all rule. I think one of the reason is that those policy tree, we use the extracted EEG features such as band power in some specific frequency band instead of using the full EEG recordings in the network. So it shows some promise of applying this type of model, even with a smaller sample size, if you're very careful with the design of architecture. And also we tune the latent layers, latent nodes. It turns out you only need 8 dimension. We don't need a huge dimension in those networks. So that's one part we're trying to improve the methodology. The second part, of course, is to have multi-stage designs. The audience here is very familiar with the SMART, and also the precursor of SMART would be the MOST designs. We worked on one of the MOST studies. And in terms of mobile health studies, so our extension is this temporal RBM. I showed you the representation visualization already. So in this study, it was depression and anxiety and both. So we're looking at the EMA measures. So the part our contribution is a very small step, is to incorporate those heterogeneity. So we have 23 items each day continuously observed for 30 days. So what we observed was the heterogeneity between groups in their temporal dynamics. So what we were trying to do is to first, there were temporal variations of RBM to account for correlation time dependence. So if you extend the temporal to temporal model, you can capture this short-term dependence. And if you add a recurrent structure, then you get to model long-term dependence. So what we did is that instead of a homogeneous group dynamics, we use a heterogeneous dynamic model. So we add an extra term to let some of those recurrent weights to have different parameters. So this is a model structure. Within each times point, we have an RBM. But there's a short-term correlation captured by this temporal structure, and also a recurrent structure capture this long-term dependence between the time points. And then these are external covariates, for example, comorbidity group versus a single disorder group, will let those dynamics to be different depending on your group assignment, your baseline group. So that's the only modification we have. And then some empirical results. We did find the heterogeneous dynamics between groups just by bootstrapping and looking at the variability of those difference between two parameters. And also it actually improves on a baseline method. So that's another direction, is the extension to dynamic models. Finally, of course, the last few minutes, maybe 15 minutes, is our extension towards using some of the real world data, for example, EHRs. So for the real world data, I think we're very all familiar with the limitations of the RCTs, but for more specific to the psychiatric patients, this is a study we did within CYMC, emergency psychiatry patients to look at whether they would satisfy the depression trials. So we ran this criteria set in emergency psychiatry patients. If we apply the top 3 exclusion criteria to these patients, we only have 6.5% patients left. If you apply the remaining 9 remaining exclusion criteria for clinical trials for depression, we only end up with 3% of patients. So a lot of patients would not be the subjects in the depression trial studies. So if we want to learn something that's have some real world impact, maybe should we learn from the real world data? So that's a depression. And then for the T2D, which is our use case for looking at tailoring treatment rules in EHRs, it's a similar story. So only like 62% of real world patients in our healthcare system, 62% will be excluded from the clinical trials for T2D. And then, if we want to learn this from the EHRs, we may be able to capture more variability in the outcomes and a broader range of the real-world medication use patterns. And also, we have probably some information on the adverse events not available in clinical trials. So this is just a slide showing we did a data quality check with colleagues in informatics department. It turns out the learning ITRs was a mental disorder is really hard from the EHRs. Only the coded data, ICD codes, CPT codes is not sufficient. You would look into the notes, clinicians' notes, do some NLP. So we started with a simpler disorder, which is T2D, and they found that for T2D, the data quality is a lot better because you have biomarkers, HbA1c, lab measures recorded. And so of course, there are many challenges. Specifically in this work, we were trying to not use inverse probability weighting. This was the method for most of the value functions are based on an inverse probability weighting form of the outcomes. So we're thinking about them, so they become unstable, especially you have many treatment combinations. Those weights can be small, and it's well known that it's unstable. So what we did is a matching-based method. So we turned the IPW-based value function into a matching-based value function. So the heuristic is that if you have 2 patients, they are matched on their confounders, but they receive different treatments, then the treatments that's associated with a larger outcome are more likely to be optimal. So your decision rule, this is an unknown function D you are trying to learn, should maximize the number of such pairs. So that's the basic heuristic. So, but you can show that this type of function under some special cases, it exactly reduces to the previous methods based on the IPW. However, what the matching gives you is some robustness and easily accommodates because you're looking at the ranking between different treatment, different outcomes, right? So that gives you a little bit of robustness. So maybe it's a little bit more robust to some phenotyping errors. And but however, in the EHRs, what we think that is we should take into account of those longitudinal structure in the EHRs. Instead of matching between patients, should we match within patients of their different longitudinal records? So this is inspired by self-controlled case series design as a CCS used for EHRs. Basically, it looks at within patients, look at all the patients with all events and whether the events are more likely to land within the exposure period or non-exposure period. So it allows us to immediately eliminate those unmeasured time invariant confoundings. So because you're matching within patients, so whatever time invariant confounding, even unobserved, they will just cancel out under assumptions. And also by looking at the patients within patients, you are more targeted at the personalized effects. So this is a very easy extension to the between subjects matching, because now we just construct our matched set within patients, and it's the same matching-based type of value function, but the only difference is that the matching set is constructed within patients. And we implemented this as a weighted classification. And then assuming some important assumptions that will allow us to learn consistent treatment rule. First is the additive model. So we can allow arbitrary function, unknown function of the baseline, including the baseline covariance, and also this is actually time-varying tailoring variable, but we can include any arbitrary form of the unmeasured confounders UI. So we relax the usual no unmeasured time, no unmeasured confounding assumption to no unmeasured time-varying confounding. So we allow the potential outcomes to be dependent on the unknown time invariant confounder. So that's one benefit of doing the within subject matching. So you can show that under these assumptions also implies no carryover effect, similar to a crossover study. And then finally, I will just show you some application results to our EHRs. So in our EHRs, we're looking at the tailoring, choosing between monotherapy insulin, monotherapy metformin, or some combined therapy. And the outcome is not the efficacy outcome, for example, reduction in HbA1c, but it's the comorbidity or adverse events related to T2D. Some examples are shown here. So it's based on 4,000 independent subjects. And then we can show that after learning those matched ITRs, we can tailor treatments to be very much beating the one-size-fits-all rule in terms of reducing adverse events rate per month. And also it shows that a lot of combined therapy were predicted to be optimal, suggesting that probably those kind of combined therapy can be beneficial in controlling for diabetes-related complications. So here is because interpretability is important. So we looked at what could be the important variables for tailoring those treatment rules. These are top-ranking variables, including we did a topic modeling of the different conditions, ICD codes, and also the co-medication codes are pretty important. What other medications our patient is on is quite important. So these are top-ranking important rules for tailoring treatment decisions for T2D. And then lastly, this is an extension to time to event outcomes under SCCS design. So I'm showing this because this shows how we do some external validation of two different data sources. One is this FDA adverse event reporting system. The other one is our CUIM and CEHRs. This is still a SCCS design, self-controlled case series design, but with time to event outcomes. So in this case, where the psychiatrist was interested in looking at stimulant use and mortality. So in FDA, our outcome was sudden death, and in CUM and CEHR, it was all-cause mortality. So two retrospective observational databases. So what we found is a consistent significant association between stimulant use and also sudden death or all-cause mortality compared to negative controls. So actually we have 30 negative control drugs. We also examined their p-values. And also these are the stimulants. So both the 4 stimulants, the combined stimulant class is quite significant in both databases. And this was found already in previous studies, but we added onto the literature is this is so-called some kind of dose finding effect, dose response, not dose find, dose response. So for the older patients, the risk is higher as expected, and these interactions are significant. So I will just stop here. Probably I went through quite, because I want to save a few minutes for the questions. Probably I went through quite fast. Just some final take-home messages and final conclusions. So what we've shown here is a few examples of feasibility of doing some machine learning methods for optimizing treatment decision-making using both RCTs and EHRs. Still, our bottleneck is that we've been doing this for the past few years, is that each feature variable seems to be having very small effect for tailoring treatments. And it's really the combination or parsing out the signal from noise that's important to look at heterogeneity of patients, variability of measurements, and doing a better compounding control. And so I already showed you some better feature extraction is helpful, especially for imaging based markers. And then something we were working on is this RL model, but for behavioral markers. So to look at how patients behave in computer-based testing in the labs, and use a RL model to learn the decision making through a hypothesized RL model and learn meaningful features such as sensitivity to reward function and also the other parameters. And then a lot of EHRs and do not have good social determinants of health measures, but these measures are available in, say, All of Us study. So that's one direction we're looking at. SOH variables, so they have neighborhood variables, healthcare utilization variables, a whole range of measures that captures social determinant of health, quite interesting. And also the last, of course, is whether we can, many groups are working on this, how do we best take the best of the both sides, RWD and RCT, and what we did in one of the previous papers to integrate both, to first extract the features from EHR, but learning the ITRs, after you extract features, learn those functional forms, use these augmented features as tailoring variables, but finally we learn the treatment rule in RCT because it's free from unmeasured confounding. So EHR is only used for feature extraction. So that's one of the ways to use both types data resources. And then this is an evaluation we're going to do in a RWD. So this is basically what types of antidepressant or depression treatments are available in RWD. So it looks like there have a lot of treatment combinations in addition to what we have in clinical trials, right? Maybe only 2 arms, 3 arms, you just study 3 drugs. But in All of Us, there are many more antidepressants, both first and second generation available to facilitate some of the ITR learning. So I just want to stop here. And of course, it's not possible without help with all the previous students, postdoc, and collaborators. And thank you so much for coming to my talk. It's been a very pleasant visit so far. Thank you.
Questions? One more.
Okay, so if I understand, the first part of your talk, using handy, and you use the items of the handy, and then you try to come up with the latent variables. And that part is just almost like a clustering algorithm, right? You just try to sort of re-represent handy scores with latent variables.
With the discrete measures. Yes.
The discrete is, my understanding is correct, right?
Yes.
Okay.
Sort of a model to do that. Yeah.
So, and then you give interpretation to the latent variables, you know, that sleep, how good is your sleep and stuff like that, right? But
yes.
But shouldn't there be like instruments already existing for these kind of constructs?
Yeah, that's a good question. We have, so there are some sub measures in depression, so subscales. You can look at that, but it doesn't do subgrouping. So it doesn't do subtyping. And so it gives you a continuous sub measures.
Oh.
So we wanted to learn those disease subtypes and do they relate to the treatment response? Yeah.
Okay, but only based on handy item.
Yeah, in this example, it's only based on handy item.
Okay.
Yeah.
So if I were gonna look at this, I would probably do something maybe boring, like a latent class or latent transition analysis approach. What is the restricted Boltzmann machine gain over something more simplistic like that?
Latent class analysis, it's also some kind of clustering as well. But so this Boltzmann machine would give you an interpretation of each of the latent states. So it gives you all those odds ratios and how do you represent a subset of measures from each of the latent nodes?
Latent class model would be the two, I think, this class is fine, but. Okay.
Yeah, probably latent class or discrete measures. We work on a lot of latent class models for continuous measures, a lot more common. Yeah.
Are they like the pending measures in your, and in one of your slides where you show there's actually a hierarchy for the elements, like they're looking them into the fast class.
You mean this?
Yeah. So how did you incorporate this known hierarchical structure into the items where they actually?
Right, actually we did it in this proposal, but what you can do is you can add another layer here. This can be multi-layered latent variables. Yeah, so if you want to enforce your already domain knowledge, you can fix some of the weights. Say you think this latent node should only be representing first three measures, you will let the remaining weights to be 0. So based on, say, some RDoc knowledge. So to include the hierarchical structure, you can add layers to those latent nodes. Yeah.
So your latent hierarchy, how does your latent hierarchy reflect your non-hierarchy between the items?
Oh, the non-hierarchy, you have to fix some of the weights. Yeah. Right, some of the structures. For example, one latent hierarchy is only between the first two nodes. And then there's another latent layer that's correlated with all latent nodes. So you can be the domain specific, another second layer latent nodes, or individual domain specific latent nodes. Yeah.
So I have a very simple technical question. I know that for all of us, data, you cannot download data. You have to run
Yeah.
and plot computer system. Then you have Columbia medical data. So how do you do data integration that when the data cannot be physically merged together? That part I didn't know.
Oh, yeah, for this is actually not between all of us and Columbia. So this is a Columbia EHR and RCT. We have
Oh,
both.
I see.
Yeah.
Okay.
But for all of us, but we can extract the functional form. If you have common variables, you
Uh-huh.
just use the learned functions, the weights to borrow more information. You can only borrow it.
Oh, I see. Okay. Mhm.
Thanks, Yuanjia. I have two questions, but the time doesn't allow us to ask one. So, I'm very interested in the individual preference weighting. I think that, in some of the applications I do, for example, there are domains like sleep or mood or activity. We ask you which one you want to improve. So you may say it's that, but actually this person may not know better, maybe this person just wants to sleep. So I wonder in this case, when you have learned the way of how to estimate the individual level preference, did you take into account of like any other empirical evidence whether the treatment actually is
Right.
working better on this domain, and we should tell this person, or just simply rely on the person's guess. Okay, I want to improve on domain 1, I don't care about domain 2 or 3, and then let's proceed, assuming that's the best for this person in estimating the goal. I'm just curious about, this process, because in other fields, this problem is so important that we don't have R to inform that. So I wonder whether R is considered as like gold or silver standard kind of data to inform the construction of these weights.
Yeah, so actually in our study, we do have R. So we can look whether the coefficient, for example, for those with a preference, how do they correspond to, is those coefficient really more important for those patients? So we can look empirically when we have R. So when we don't have R, then that's a very difficult, right, to have a weight function that can capture something that's consistent overall, especially like you said, if the what patient thinks is not what actually happened.
Yeah,
The-
so that's correct. So
Yeah.
I wonder if you're trying to extend this to multiple time points. Maybe in the first two time points, you learned, hey, this treatment is really helpful with valence. But according to the R data, maybe you're not indicating that as your preferred domain to optimize. I think it could be good to have a mechanism to bring in the data-driven evidence that, hey, this may be working for you in the valence, but you did not say you prefer that. Let's change the rule. So I think that could be very interesting.
Right, like a dynamic multiple time point decision point. Yeah, yeah, that's a great suggestion.
In reinforcement learning, there's one called the universal reinforcement learning. Basically, you get feedback, you try to figure out what's reward from treatment.
All right, let's thank Dr. Wang again for the fantastic presentation.